It's my utmost pleasure to introduce our next speaker, Kyunghyun Cho, or Cho as he is known to most of us. I've known Cho for about 5 years. We met towards the end of 2013. I was just wrapping up my time with Yoshua Benjo in their lab, and Cho had just started there as a postdoc. And this was right at the time, right after the ImageNet breakthrough was made in 2012. And everyone was focusing on the next frontier, which was machine translation. And everyone knew that they wanted to do some kind of encoder-decoder architecture to crack machine translation, but they didn't know how to actually make it work. And Kyunghyun was central to actually making recurrent neural networks work in the framework which became known as sequence-to-sequence learning, which has since spawned an entire subfield of research and has had wonderful knock-on effects. Since 2013, Cho went to NYU, where he started as an assistant professor in 2015, after 2 years with Yoshua's lab. And in 2016, Cho joined Facebook as a research scientist. Yep. So it's a wonderful pleasure to introduce Cho, and please give him a warm welcome.
Well, thanks for the overly generous introduction, Stefan. So what I'm going to do is, today I have 2 hours, and then fortunately I have another 2 hours, that's not going to for everyone on Thursday. So I'll try to, cramp the entire semester worth of the material into these roughly 4 hours. So let's see how well I can do. And then it's always kind of, let's say, difficult to measure, at which level, and then, from the what kind of point that I should start. But I'm going to go with a very straightforward, let's say, supervised learning setting, and then how the same setup for the supervised learning can be used for the unsupervised learning, and then, all the way to the text generation, machine translation, and so on. So we need to talk about supervised learning. You probably have heard about this setting over and over already this week, but, it's because it's important. I think it justifies for me to, to repeat it again. So what we are provided is a set of n many, let's say, input-output training examples. So the input can be some arbitrary vector or the sequence. Output, in this case, we are going to say just one of the categories out there. And then we define a per example loss function. Either we define it, somebody else is going to give me that. You probably heard about, how to use a softmax and then put the cross-entropy loss during the practicals. And then for the different types of things, you may have heard about the ranking loss and so on. And then what we have, in addition to the training examples, is 2 separate sets of the examples, one called validation, and then the other called the test sets. And then I'm going to talk about, how they're used, and then you probably know already, but this is perhaps the most important thing, especially if you want to build a machine learning system and then deploy it in the real world. And then once these 3 things are provided, what we need to decide is, okay, what are the hypothesis sets or the spaces from which we are going to find our final model? And then I'm going to talk about this a bit more. And then once we have defined the set of hypotheses or these hypothesis spaces, then we need to come up with some kind of learning algorithm. And then I'm going to talk about the learning as optimization only. Obviously, earlier today, you probably heard about the Bayesian approaches and so on. But, for now, we're going to stick to the simplest thing you can think of. So, most important, so if you think about what supervised learning is, it's all about how to build an algorithm that's going to find an appropriate algorithm that solves your problem. So it's kind of, let's say, one step beyond what you usually learn about the algorithms in your, let's say, undergrad computer science courses. So what we need to do is that, okay, someone is going to decide on the set of all possible models, and then we are going to call that set a hypothesis set, and then each of the model inside it is going to have, one hypothesis. And then what we want is that within that, we need to find the best one within that set, and then that we use the optimization algorithm to do. And then what that corresponds to do is, as written in the slides, so it's kind of, let's say, I don't know, can you see my pointer? Let me just try. No, right? Yeah, I know. I'm trying to figure out how to. Okay, can you see my pointer from the other side? No. Okay. Yeah? Yeah, okay. All right, so this is kind of cool. Okay, so you see the equation here. So what we are doing is to use the optimization algorithm to search within the hypothesis set. And then within that hypothesis set, our criterion for search is to minimize the sum of the per example losses across the entire training examples. Now, and then this is done based on, this is based on the training set. So we had the 3 sets, right? One training set, validation set, and the test set. We're going to use the training set. So this allows us to find one model within the hypothesis set that's going to solve the problem as well as possible. But then the issue is that we are not going to consider only a single hypothesis set. We're going to consider multiple hypothesis sets. I'm going to talk about what those hypothesis sets will correspond to soon. And then what we need to do is, among all those, it's kind of difficult to see from the other side, but okay, among all those models that we have found, so we had all those hypothesis sets, and then within each of the hypothesis sets, we found a model that's going to minimize the loss function on the training set. Now we need to decide among all those models that we have found, which one do we use? So that's called the model selection, and then there, what we do is we're going to choose one with the lowest loss function on the validation set. So this is where the validation set is going to be used, and then that is validation set has to be only used for the model selection, not for the optimization. So search within the hypothesis set, we use a training set. Search across the hypothesis set, we use a validation set. Well, that's good. But then, because we use the validation set already to find the best hypothesis set itself, we cannot really report a validation error and then say that, this is the model, and then this is how it's going to work in reality, right? We cannot really say that because there's already a bias from using the same set to select, and then you cannot use it to report how well it's going to work in practice. So to do so, we need to have a separate set called test set. So this test set, you're going to just, construct the test set, put it aside until the very end, and then when you have the final model, right, so after the training and the model selection, you're going to use the test set to see how well this model does, and then report it, or use it as a guideline on how well your model is going to do. Now, this is really interesting, especially in the text domain. One thing we know is that the text is the kind of data that is generated like every day or every minute or every second. If you look at the social media, there's a text, like newly created every moment. If you look at the newspaper, there's going to be a new news article every minute or even every second if you consider the entire world. Now, what it means is that there is no such thing as the fixed underlying distribution in the case of the natural language. In fact, the distribution constantly drifts. So if you think about what kind of topics that people talk about in the newspaper or the news articles in 1980s, half of the things we don't care anymore, for instance. And then if you think about what kind of things that people are going to talk about in 20 years from now, half of the things we cannot even imagine. What it means is that we have to be really careful, especially when it comes to natural language processing and the text classification, on how to build these test sets. So often what we do is we do not try to actually stick to the assumption about the test distribution, training distribution, all those distributions are same. Unfortunately, because that's not true. So what you usually do is that when you have a data, you're going to ensure that your training data is from the earliest years. Your validation data is going to be from the following years, and then your test data should be from the consist of the most recent articles or the text you have. Now, then that is the one way to actually evaluate how well our model is going to generalize to the future topics or the future text or the drift of the topics. Of course, if you're working on the historical document or the historical text analysis, then you probably want to do the other way around, right? So you want to use the training sets from the future and then test it on the past, and then hoping that your model is going to generalize to the earlier topics so that you know that you can use that model to do the historical data analysis. So let's talk about a bit more details before we delve into the actual text, because at the end of the day, natural language processing, really all we see is just a sequence, not really the actual text. So that's why we have to focus on this part. So what do I mean to decide or to choose hypothesis? In the case of the neural nets, a single hypothesis set corresponds to how you design your network and then what kind of hyperparameter you're going to use. So let's say if you decided to use the AlexNet, obviously nobody should do it these days, but then that's going to give you one hypothesis set in which you need to find the best model by doing this stochastic gradient descent, or another hypothesis set. So as I said, we need to have a set of hypothesis spaces. Another one could be, let's say, using the GoogleNet. Again, this is also pretty old, so you shouldn't use it. But but you see the idea, right? So there are going to be multiple hypotheses that you're going to create within that. So that hypothesis sets are the neural nets. Within that, you're going to use the optimization algorithm to find a good one. And then inside each of the hypothesis set, in the case of the neural net, each point in the space is characterized by the parameters or the weight values and bias values. You have already learned about it yesterday and so on. And then there are infinitely many of them, so the optimization is quite tricky. But before going into the optimization, what does it mean to build a neural net? Is in fact, at the end of the day, it's all about how to build a directed acyclic graph, where that graph, if you start from the beginning nodes and then compute it all the way out, then it's going to give you the output of the function. And then each graph is going to have both the, let's say, sorry, it's not easy to read, like the other way around. So we're going to have some of the input variables, so the variables that you get as the input, and then you're going to have the parameters node, and then they're going to be all connected with the edge via these squares that correspond to some kind of computation, and then you just build a neural net. So in fact, we call it neural net because it's kind of, let's say, of the historical reason, but at the end of the day, it's all about how to build a computational graph that is going to be directed, so we know in which order the computation needs to be done, and then there's no cycle in it. So if you think about it, in fact, most of the algorithms or the models in the machine learning can be framed as a computational graph. So, like you probably have heard about and then probably have used a lot of the logistic regression that is used to take as the input and then give you the probability of whether that input should belong to the positive class or the negative class. So it's a binary classification. That's really nothing, but you start with some input, right? So there's the input node, and then you're going to do the dot product between this input and the parameter, and then the output is going to be added with the bias, and then eventually you apply the sigmoid function so that you get the probability of that example belonging to the positive class. And then if you have done some simple, let's say, polynomial regression type of thing, third order polynomial regression, you can again draw this as the directed acyclic graph. So this is a really nice, way to abstract out your model's computation. And then once you have the directed acyclic graph, that you don't have to actually build it yourself. Let's say somebody just gave you this directed acyclic graph. Then what you do is you need to first know how to use it. And then that's really nothing but topological sweep. You do the breadth first search. You start from the input variable nodes, and then you do the computation over and over until you end up at the very end of the graph. So in the case of the logistic regression, we start from the input nodes, which are going to be the actual input x, and then the weight vector w and the bias. You compute the dot product first, you do the addition, and then you apply the sigmoid function, and that's going to be your logistic regression. So it has a really amazing implication in practice, especially because it naturally supports a higher level abstraction. You really don't have to care much about how each of the node and then how the sweep is computed in reality. All you need to know is that, okay, so here's a nice framework that allows you to build that kind of computational graph, and then the computation itself is going to be done somehow under the rug, maybe like distributed, maybe on a single CPU, maybe on a single GPU, somehow, but you can work at this higher level of the abstraction without worrying about how the computation is actually done. So this is how you do it, and then the nice thing is that all those, let's say, reason frameworks, I think that the Indaba is currently using TensorFlow. Bad idea, gotta use a PyTorch, right? But PyTorch. But there are PyTorch, TensorFlow. There is something called DyNet. There used to be something called Theano as well. And then all those frameworks allow you to just think about all these neural net, how to build a neural net from a very high level abstract level, high abstract level. And then those frameworks are going to do the computation and the optimization for you. So now, once we have defined the hypothesis set, we need to define a loss function. And in order to do so, we usually look at a so-called decomposable loss. So our final loss function is going to be sum, or the average, of the per example loss functions. So, and then there are so many loss functions, and then how to define a good, robust loss function itself is the entire one huge discipline in machine learning. If you think about classification, there's hinge loss, for the vector machines, log loss, that's going to be the cross entropy loss with the softmax, and then so on and so on. For the regression, it gets even messier. So there is the usual mean squared error, but maybe that's not robust enough. So maybe we should use the mean absolute error. Maybe we can come up with a better robust loss function, and then so on and so on. But then the nice thing, you probably heard today earlier about the probabilistic thinking of the machine learning. The nice thing is that if you put everything into the distributions, probability distributions, then the loss functions actually automatically just falls out of the definition itself. So what do I mean is that in the supervised learning, and then this is going to be connected to how we do the text generation eventually, is that in the supervised learning, any kind of supervised learning problem can be thought of as trying to predict or to build a machine that's going to output a conditional distribution over the all possible output given some input. Because once you do that, now you're going to pick the output with the highest probability, or pick the expectation over the conditional distribution, and then that's going to be the actual output of your supervised learner. And then there are, let's say, a bunch of other distributions that you can think of, especially in terms of the supervised learning, but we're going to just look at two distributions quickly for the classification, because at the end of the day, all NLP does is to just do a lot and a lot of classifications. Just don't tell other NLP people, but that's the, like the inconvenient truth about it. Okay. So the most important distribution, I think, is the Bernoulli distribution. So Bernoulli distribution, or the Bernoulli random variable, is defined to be a binary. So it can take as a value either 0 or 1. And then it tells you what is the probability of this random variable being 1. And then that is the only parameter you need. And then the parameter, which I'm going to denote as the mu, is going to be some value between 0 and 1. And then we're going to use this kind of sigmoid function to ensure that whatever is outputted by the neural net is going to be between 0 and 1. And as soon as this neural net outputs this mu that characterizes the Bernoulli distribution fully, then suddenly our neural net is outputting the conditional distribution that is Bernoulli variable, right? So what we do is that we can, as we said, it's just a directed acyclic graph, so we're going to, throw in some arbitrary graph once a while, because as long as it's directed and acyclic, it doesn't really matter how complicated or how simple that is. And then at the end of this arbitrary graph, we're going to get a single real valued number, and then that real valued number is going to be fed into this logistic sigmoid function. So x is going to be the input, y is going to be the output. It's going to be 0 as the value gets smaller and smaller. It converges to 1 as the value gets larger and larger. And then now we have the model of the neural net that's going to output a Bernoulli distribution. Now, but the binary classification is kind of less interesting, right? So, where can you use the binary classification? Maybe in the recommendation system, should I recommend or not? But, more interesting thing is, how to make it into a multi-class classification. So you can think of okay, so let's say you're an editor of some kind of newspaper that is gigantic. You have, let's say, tens of the thousands, let's say, journalists sending you all those articles every day. And then those journalists tend to be sloppy when it comes to, which section the article should go in. And then maybe you can build this kind of machine, let's say, text categorization system that's going to tell you exactly which section the article should go in. And then there are going to be more than one sections. So and then there comes the categorical distribution, which is a generalization of the Bernoulli distribution. Instead of having 0 or 1, now we're going to have C many classes or the categories. And then in order to characterize this distribution, we need the C many numbers. But with the constraints that all of those numbers needs to be higher than 0, and then they all sum to 1. And then it turned out that in 1992, I know it's going to sound weird, this softmax normalization function was proposed and published at the conference NIPS in 1992. I know, how can you write the NIPS paper out of, defining a softmax function? But, that just tells us, how quickly we have evolved in time in this field. So the idea is that whatever the graph that you have that's going to take as the input some set of parameters and the input, this graph is going to give you C many real values, right? So it's going to be a C-dimensional real valued vector, and then the vector needs to go through this softmax function. So first you exponentiate each of the values, so that it's going to be non-negative, and then what you do is you're going to divide each number by some of them, so that eventually what you get is the set of probabilities that fully characterize this categorical distribution, and then there you get the multi-class classifier. And okay, these distributions are nice, but what did I mean by, okay, these distributions give us automatically what kind of loss function we use. So it turned out that what we want to do, once we have the distribution, what we want is for that distribution to put as high a probability mass as possible on the training examples. So I have the one example that has the input and the output. What I want is that I want my neural net, or the directed acyclic graph, to put as high probability as possible on the correct output, while minimizing the probability of all the other values. And then that corresponds to maximizing the likelihood of the parameters. So, you probably heard about it earlier. So the likelihood is of the function of the parameters, or you can think of the function of the function, but function of the parameters. And then that function is defined as the sum over entire training examples. And then that sum is of the log probability of the correct output given the input. And then the distribution is given by your directed acyclic graph and then your choice of the distribution. So why do we use log? Okay, that's a good question. You probably heard already. I missed the earlier talk, but I did many reasons, but largely computational. But this is way out of my lecture. So then equivalently, because the optimization people like to minimize things rather than maximize things, so what you usually do is just put the negative sign there and then satisfy the optimization people that, okay, we are minimizing something, so we can use any of your tools off the shelf, right? So, and then there is another nice practical implication is that all those distributions have already been implemented in these frameworks, right? So the PyTorch implements all those distributions, TensorFlow implements it, Theano implements it, and then subsequently, they have all implemented the negative log likelihood loss as well. What it means is that all you need to do is trying to figure out which distribution your problem requires, and then put it at the end of your graph, and put the loss block at the end. What do I mean? So we had the logistic regression here. What we need is that we know that this is going to output a Bernoulli distribution. We're going to simply add in the negative log likelihood block, for instance, from the PyTorch. And then this block is going to take as the input what has been predicted, and then what is the correct answer. And then this block is going to try to maximize or give you the probability or the negative log probability of the correct answer given this neural net. And then you can use that to change this part to maximize the probability of the correct answer. So then the question is, how do we optimize the loss function? I'm not even, qualified to, talk about the optimization, but let me try to, give some, simple idea. Is that it's a infinitely large hypothesis space, and then within this infinitely large space, we need to find one point. It doesn't have to be infinitely large, but let's say it's infinitely large, and then we need to find one point there. And then what we are going to do is, in other words, we cannot really do the exhaustive search. You cannot really check everything. Of course, these days, people started doing those evolutionary algorithms, and they kind of check everything, but okay. But we don't really want to do that. If we know how to do it more efficiently, why not? Right? So what people have been doing is to use the information of the gradient that tells you at one point in the space, locally, which direction you need to move in order to decrease your objective function little, or increase your objective function little. Is all about just adding the negative sign. And then what people have been doing is that, okay, so let's try to figure out how to compute a gradient. Once the gradient is there, we can use the simple gradient descent, stochastic gradient descent, or any kind of off-the-shelf optimization algorithm you can use. Now, that's where the backpropagation comes in. If we make a directed acyclic graph with all those computational nodes that are almost all, let's say, differentiable almost everywhere, then it turned out that we can use the chain rule of derivatives to come up with an algorithm that's going to compute the gradient of the output or the loss function with respect to all the parameters in the graph automatically. And then that's the entire idea about the backpropagation. And then, as you can see here, all you need to do is just know what this chain rule of derivative is. And then what the chain rule of derivative tells you is that if I change something in this kind of, let's say, chain of the functions or the composition of the functions, what I need to know in order to see what happens at the end, I need to know at every step what happens if I change the input to that step, to the output. I'm going to talk about it a bit later more in terms of the recurrent neural nets and so on. But what it means is that eventually all you need to do is for each of the computational block, so you don't really care about how to compute the gradient of the entire graph. So for instance, if you wanted to compute the gradient manually of the entire, let's say, inception network that I showed you earlier, the Google net, that's going to be a pain in the ass. It just takes so much time. And I guarantee you, you are going to make a mistake. There's no way someone can write the gradient and then compute it without any mistake in the first try. And then you're going to try to recompute it manually. You're going to make another mistake, right? So it's kind of impossible at some point. But then what happened is that for each of the computational block, we can write the Jacobian, or more so, the Jacobian vector product. And then what this Jacobian vector product tells me is that, okay, if I know what the gradient of the loss function up to my output, then how can I actually pass that information back to the previous node? And then what you need to do is you need to multiply that vector, whatever you have received so far, with the Jacobian of the computational node itself. And then the Jacobian tells you what happens if my input is perturbed to the output. So if I perturb the input, what happens to the output? And then that's what you need to multiply in order to tell the previous nodes that, okay, the loss function with respect to your output is going to change like this if I perturb this. So now try to multiply your Jacobian there. Now, nice thing is that all these things have already been implemented in those awesome frameworks like the PyTorch, TensorFlow, Theano, and so on. What it means is that all you need to do is you build the forward computational graph that goes from the x, y, and the parameters all the way to the loss function, and then you ask your framework to, okay, please compute the gradient of this loss function with respect to my parameters. Then what it's going to do is it's going to start from the final node, the loss node, and then pass its gradient back. And then at each computational node, this computational node is going to multiply its Jacobian to this past gradient and then pass it back to the previous ones. And then eventually you get you automatically get the gradients of the loss function with respect to the parameters. Once you have that, then it's just you use the off-the-shelf gradient-based optimizers, except that it turned out that it's not that trivial because our data sets are often really large. We have, let's say, millions or billions of the data points. And then as we talked about earlier, it's a decomposable loss, meaning that we need to actually compute the loss for every single example in order to get the single loss function. And then we can. And then what is the property of the gradient is that it's only locally valid. So the direction that you're going to based on the gradient or the negative gradient is going to be only locally valid. And then you need to take a lot of steps to find the model that's going to do really well in your training set. But then every time you have to take compute the gradient, you have to compute the entire thing. It just doesn't make any sense. So people started using the stochastic gradient descent. I'm pretty sure you have learned how to do that in the practicals, right, Stefan? Yeah, you taught them, yes. So I'm going to skip it, yes. So this is what you do. But only one thing that I want to point out is that you never want to to minimize your function at the end of the day, right? So you never want it. That was never a goal. So minimizing the loss function that was computed using the training set was never a goal. So what you want to do is you want to stop optimization earlier than the optimization algorithm tells you to do. So just graphically saying, so this is going to be my last slide about the supervised learning. So bear with me. So this is the hypothesis space you're going to get by defining one directed acyclic graph. You start from some random points. You're going to try to follow the gradient steps. And then let's say this was the point where the loss function computed on the training set is minimized. But that is precisely where you don't want to be. And then because once you're there, that is called overfitting. What you want is that you want to stop at a point that is near the minimum of the validation loss. So how does it work? What does it mean is that essentially from every point, there is a small subspace of the hypothesis space that is reachable by a single step of the optimization procedure. And then you can think of that small subspace as a new hypothesis set. And then you have so infinitely many hypothesis space on the path of the optimization, and then you are going to select one based on the validation loss. So you have to do the early stopping. And then I see a lot of submissions that say that, okay, here's two different models, and then two different optimization parameters, but somehow they are going to say that, okay, we're going to use the exactly same number of the optimization steps and then report the test error and then say that one of them is better. Then I'll be like, but how do you know that if one of them either overshot or undershot the correct, let's say, point where you should have actually stopped? So this is really important thing to do, especially in the stochastic gradient descent, and when you have enough data. When you have a very small amount of data, that's where you want to be Bayesian, I guess. And then they're trying to marginalize out everything, right? So this is where I'm going to stop talking about the supervised learning and then finally start talking about the text classification. But is there any questions up to this point? No questions. That's good. That's good. That means that whatever I said kind of got through to you, right? Fully. All right. So, or either that or it was very boring. Okay. So let's go to slightly more exciting part that I was supposed to talk about. That is natural language processing, and then how we use this kind of machine learning techniques for the language. And then as the first step, what we need to figure out is how to do the classification. So the text classification is just like the supervised learning, as in input is going to be some kind of natural language sentence or paragraph. We're not going to distinguish between sentence, paragraphs at the moment, because at the end of the day, those are just sequences. And then output is a category to which the input text belongs. And then we are going to simply assume that there are a fixed number, C, of categories. So some of the examples include, let's say, sentiment analysis. Is this review positive or negative? Or, text categorization, which category does this blog post belong to? Can we actually automatically decide that? Or, there are some of the intent classification. For instance, if you're building a chatbot-like of thing, you want to know what is the intention of the user based on their utterance. Is this a question about a Chinese restaurant? If you can tell, then that actually allows you to answer in a consistent way, right? That's going to talk about the Chinese restaurant, not of any other restaurant. Now, so all the things that I talked about during the past half an hour applies here, except that we need to think just one bit about how to represent a sentence. In the case of images, it's quite the natural that an image is a tensor, right? So it's going to be the, let's say, three-dimensional tensor. You have the height, width, and then channel, and then for each of the point, you have the intensity value. Or sometimes you can use a different way to represent each of the pixels, but it's very natural that you get a very fixed, nice size vector or the matrix representation. But in the case of the sentence, that's not necessarily true, because a sentence is a variable length sequence of tokens. So some people say, oh, you just use the maximum length. So that can work if your domain is narrow enough, and then you know about the topic, then you can tell that. But if you want to build a really generic machine learning model that can handle any kind of language, regardless of which language, which topic is going to be about or the written about, then we really have to work with the variable length. And then each token could be any form of vocabulary. So I'm going to say that, there is some fixed vocabulary of all possible unique tokens, and then a sentence is going to be simply a sequence of the tokens taken from the vocabulary, right, with replacement. So for instance, I put some examples in Korean. When do you ever get to see the Korean sentence, right? So what it says is that, Cape Town에서 강의 중입니다. It says that, I'm lecturing in Cape Town. Well, it's not Cape Town exactly. I didn't realize that when I was preparing this slide, but I thought it's going to be in Cape Town, but okay. And then now you can decide that, this sentence, you're going to represent it by simply dividing them using the white spaces. So I'm going to use a white space here, white space here, white space here, white space here. I divided them, separate them, and then it's going to be a sequence of those white space separated tokens. Or maybe, it just doesn't make any sense in the case of the Korean. Maybe what I want to do is I want to separate out the suffix from the token as well. So in the case of the second token here, this part is town, so that's going to be the town of the Cape Town, and then this suffix corresponds to, the in the kind of thing. So then perhaps what I want is that I want to cut this out into the separate tokens. Okay. But then, somebody might say that, but that's too, the inconvenience. So how do I figure out what is the suffix, when the suffix starts, and when the prefix ends, and so on, right? So then maybe, what you want to do is you just use every single letter separately, right? So we're going to say the first, let's say, syllable is going to be one token, second, third, and then blank symbol is going to be another token, and all the way, perhaps. Then somebody is going to say that the Korean is a kind of very compositional letter, so you can actually, they decompose each of these syllable into the, let's say, 3 parts. So maybe we should use that. Then somebody's going to say, no, but we're computer scientists. Maybe what we need to use is a Unicode. Or at the end of the day, it's all bit streams, so maybe we should use the bit. Now the interesting thing is that this is the discussion we have, but this is not how the neural net sees a sentence as. What neural net is going to see is a sequence of integer indices only. So we're going to somehow build a vocabulary of unique tokens, and then we're going to have some way to turn a sequence or a sentence into a sequence of integers where each of the integer refers to the entity in the vocabulary. So for instance, if I decided to use this kind of representation, so let's say morpheme-based representation, I'm going to build a vocabulary of all the unique tokens that I get from my training set, and then I just turn it into a sequence of integers so that for each of the tokens, so for instance here, this SO is going to correspond to integer 20, and then this integer sequence is the only thing that neural net looks at. Neural net doesn't really care what actually we think. What it means is that this gives us a very nice, another way of abstraction. So how we tackle each of the language in order for us to turn a sentence in whatever the language you're working with into a sequence of integers. Now that one is up to you and depends on the language and the problem. But then from there on, this very same technique is applied to any language or any problem that you can think of. So okay, integer indices. But the thing is that, I don't know, I'm pretty sure you haven't really heard from the Indaba yet, how to represent the integer, right? So what does that integer correspond to? And then if you just in the case you speak any Korean a bit, and if you look at this vocabulary, which I just built in myself, these integer indices actually have absolutely no correspondence to the actual similarities between the tokens. Because it's just a one-dimensional line. How are you going to, sort all those tokens according to their similarity in a one-dimensional line? It's impossible, right? So those integer indices are very arbitrary. Often what we do is we're going to sort it according to the frequency of each of the token, and then the more frequent the token is going to get a lower integer numbers, and then, the rare ones are going to get a high integer number, but it doesn't really matter. Integers are just there for us to recover or transform the token into the, some, let's say, neutral representation. So what we use is so-called one-hot vector. So we wanted the most neutral representation that we can find. And the one-hot vector is simply a vector. It's going to be a binary vector whose dimensionality corresponds to the size of the vocabulary. And it's going to be all 0 except for a single entity, which is going to be set to 1. And then that entity's index is the index of corresponds to an integer. So this is going to be a kind of typical way of representing the one-hot vector. The most important property of these one-hot vectors is that they are all equally distant from each other. You pick any of those integers, turn it into the one-hot code, and then all the other integers are distance square root of the 2 away in terms of the Euclidean distance, for instance, if you want to compute it. You pick another one, the same thing holds for everything. In other words, we are trying to represent the text in a way that is most neutral and then does not have any kind of, let's say, language-specific or the domain-specific property. Now, of course, that does not mean that, these neural nets can do, anything without knowing about any of those tokens. So how does the neural net trying to get the meaning or the similarities among those tokens out of it? So that's a big question. And then, it turned out that what we can do is we can associate a single vector. So that's going to be parameters that are going to change over time as we do the training. Single vector to each of the token. And what does that mean is simply we're going to have one gigantic matrix, which is going to have, let me see, so I have the transpose there. So as many columns as there are tokens in the vocabulary, and then each column corresponds to a vector assigned to that word. And then those vectors are all going to change. And then, if we use the one-hot vector, if we simply do the multiplication, so we're going to do the matrix, that W matrix, often called embedding matrix, times this one-hot vector, that is exactly like simply slicing out one of the rows or the columns from the embedding matrix with the integer index you have. So that's how the neural net internally is going to represent each of the token. And then based on how those vectors are arranged, or how the vectors are close to each other, the neural net is, based on that, neural net figures out what are the tokens that it can consider as equivalent, or what are the tokens that it should consider as very, very separate from each other. So often we call this layer embedding layer or the table lookup layer. And then this is like at the heart of the natural language processing and the deep learning these days. Any questions at this point? Is it all clear, like how this table lookup works? Okay. Yes. So, you will get to that hopefully later today. Yes. So the question was about how do you actually build a vocabulary? I'll get to that, like when I actually talk about what we do with the machine translation or language modeling. Yeah, I'll get to that. Any other questions? My lectures tends to be very, very clear, right? Yes. Makes sense. Makes sense. Now, but that was, so what we just talked about is how to turn those token indexes into vectors so that the neural net can do something about it. But the question is, okay, how do we build a neural net that's going to combine them so that we get a single representation for a sentence? So the simplest way, it turned out, is something called continuous back-of-word, or the CBOW. And then, like after the table lookup operation, what you can think of it is that you have turned the sequence of tokens into a sequence of token vectors. Now, in the case of the continuous back-of-word, as the name suggests, back-of-words, we're going to simply ignore the order of the tokens in a sentence. And say that, okay, this is a bag of all those tokens. And then we have a bag of token vectors, and then we're going to simply take the average of those token vectors. And the nice thing is that the averaging is a differentiable operation, right? And then can be computed extremely efficiently. So we can just plug it into whatever the directed acyclic graph you're making, right? So we're going to start from the sequence of tokens, turn it into a sequence of vectors, add in the averaging operator, add in the and then have some arbitrary directed acyclic graph, and then you add in the softmax, and then you get a like the text classifier. It's extremely effective in the text classification. It's kind of, let's say, surprising because the order of the tokens is completely ignored in this case. But when it comes to text classification, like the Drang classification, intent classification, like the sentiment analysis, this turned out to be extremely effective. So you'd get, let's say, 90% of far with just a continuous back-of-word. There will be, some corner cases, but, it turned out that much of, like classification can be done simply using the back-of-words. And then, that have been shown by the bunch of papers recently, and then, everyone was, all confused, right? Why is the order not mattering, this at the end of the language? Of course, for the generation and more sophisticated problems, it turned out that the order does matter. But for the very simple classification, it turned out that the order kind of doesn't matter. So in practice, you do not implement this yourself. What you do is you're going to download the fast text from the Facebook AI research. This is potentially the most efficient implementation I've ever seen. I don't know. So I look at the code, I couldn't understand, how it was implemented. It's that optimized. So, and then it's really heavily optimized toward the text classification. So, that's going to get you really far, even with a gigantic data set. Let's say if you have the entire Wikipedia with the fast text, with only the CPU cores, let's say 20 or 40 of them, it's going to actually solve the things in a few hours only. So, go use the fast text. Or, you can use the Valpa-Webit as well. But, who uses it anyway? Right? So let's just look at how you build it, right? So you start with the sequence of token indices, right? It's going to be a sequence of the integers. And then each one of them is going to be turned into a token vector using a single table lookup layer that shares the embedding matrix. So we're going to have a single embedding matrix. We have the average operator. And then after that average operator, what we get is a vector representation of the sentence itself. And then from there, we have some arbitrary subgraph that has its own parameters, right? You can have the multi-layer perceptron on top of that that's going to output a real valued vector whose dimensionality is going to correspond to the number of classes you have. And there, the softmax normalization is applied so that your network is giving you the probability or the categorical distribution over the categories given the source sentence or the input sentence. So that was good, but obviously continuous backward is not satisfactory because we're ignoring the order. And then we all thought that the language matters because there is the clear ordering and the strong dependencies and so on. So what we are going to now look at is so-called skip bigrams. But skip bigrams, not fancy enough. So we're going to stick to the term that was introduced by the DeepMind called the relational or the relation net. So, but this is skip bigram. So the idea is that we're going to look at, so it's a bigram, so we're going to look at 2 words at a time. We're going to look at a pair of tokens at a time, but then we're not going to look at this consecutive pair. So we're going to look at every possible pair of tokens in the sentence. And then given some arbitrary pair of tokens, we're going to have a relational net module that's going to take as the input these 2 tokens. So initially, it's going to be the token indices, right? We are going to have the 2 integer indices. They're going to be turned into the 2 vector representations, 2 token vectors, and then they're going to be transformed and summed. Some nonlinear function is going to be applied, after which we apply another matrix multiplication to get a vector representation of the specific pair. And then we're going to compute that for every single pair of tokens that you can think of. So we're going to go through every single pair and then compute, use this relational module to get the representation, and then compute the average or the sum or the max operation, as you learned yesterday from the convolutional net lecture. So we can use some kind of pooling to get a single representation. Excuse me. And then, of course, you can think of generalizing this to the triplets instead of the pairs, and then like even more, but this is going to be done at the expense of the computational efficiency, right? Because it's going to grow exponentially, where the power is going to be the number, the size of each of the triples you get. Now, graphically saying, if you look at how it works, we have a sentence that's going to be a sequence of integer indices. We're going to make 2 copies of that. We're going to consider every pair, and then each pair is going to fit it into a single relational network module, and then that's going to give you a vector. So you get quadratic number of the vectors, and then we use the average, max, or some kind of pooling operator to get a single vector representation of the source sentence or the input sentence. We have the arbitrary subgraph as usual that's going to output a real valued vector, and then the number of the values there has to correspond to the number of categories. You apply the softmax normalization function to get the actual conditional distribution over there. So this is good, but again, this is slightly less satisfactory in a sense that we are treating every pair of tokens, regardless of how close they are, how far they are, or how relevant they are. We're treating all of them equally, so it's not that satisfactory. So then there comes the convolutional network. Yesterday in the Nalia's lecture, I heard one question about, okay, so how can you apply the convolution to the sequence? And then Nalia said, oh, all the examples were sequence. That's true, right? So what we can do is we can use the convolutional network from the yesterday's lecture just as it is to the sentence representation or the text classification. And then it does have a kind of, let's say, nice story here. So if you think about what convolutional net layer is, that it's going to look at a local patch or the local n-gram, and then trying to summarize it into some kind of vector representation. So, okay, so you're going to start by looking at pairs of the consecutive tokens, and then if we have another layer on top of that, now we are looking at a slightly larger chunk of text at a time. And then we can add more and more. Eventually, we're going to have a convolution layer that looks at the entire sentence. And then that kind of corresponds or agrees well with how we view how the text should be processed. We go from tokens, and then we're going to probably chunk them into the multi-word expressions. For instance, New York is going to be a very typical example of the multi-word expression. And then we're going to chunk them into the phrases, right? So we have the verb phrase, noun phrase, all those things. And then probably we're going to make it into the sentential phrases. So if I use and in the middle, often I have the 2 sentences that are just conjoined using the and a single sentence. So I probably want to process the first sentence and the second sentence separately, and then eventually I combine them to get a single sentence. And it seems like stacking these convolutional layers corresponds very well to how our intuition of how things should work. And the nice thing is that all these convolutions, extremely efficient implementations are available for CUDA as well as even for the CPU. And then some Intel compilers nowadays support a very efficient convolution with the many CPU cores. And then those are all implemented in the framework. All you need to do is just build a directed acyclic graph where you're going to have the convolutional node, or the 1D convolution in this specific case, over and over. And then, it turned out that just doing the convolution actually doesn't work well, especially for the text classification. What you want to do is the so-called with convolutional layer. So you're going to have a convolutional layer, multiple of them, in parallel, and each one of them is going to have a different kernel width. So some of them are going to look at 2 tokens at a time, some of them are going to look at 3 tokens at a time, some of them are going to look at 4 tokens at a time. Now then, you can actually efficiently summarize the multiples variable, let's say, size, let's say, phrases very easily. And then because, excuse me, stacking them is nice, but, you need a lot of, let's say, layers to get it done. So, in fact, you learned it yesterday, so there is a dilated convolution that works really well. And then using some gated convolution layer is good, but we're going to talk about this soon if I speed it up a bit, okay? Now, convolution is nice, but still not really satisfactory. This fixed nature of the local receptive field is not that great. I mean, sometimes you need, let's say, you need to look at 3, sometimes you need to look at 4, sometimes you need to look at 8. But how do we decide? How does the convolution layer decide? Of course, everything happens in the high-dimensional vector space inside the neural net. All those magical things can happen, but perhaps we can be more explicit. So it seems like convolutional network and the relational net, they have their own strength and then their own weaknesses, and then they're kind of complementary to each other. So let's think about what the relational net does is that for the representation or the vector you're going to get at location t, what you're going to do is you're going to look at all possible pairing of that t token against all the other tokens, and then get the vector representation and then sum them. The average, it doesn't really matter. Let's say sum. On the other hand, what the convolutional network is going to do is, okay, given the current token, we're going to only look at the nearby ones, right? We're going to ignore anything that is far away. Now, what that means is that you can rewrite it as a sum of all possible pairing, but then there's going to be the weighting of either 0 or 1. So the nearby ones are going to have the weight of 1. Further away ones are going to have the weight of 0. So that's how it's written. And then now you see the connection to the relational network, and then how we can combine the convolutional network with the relational network. Oh, thank you. How did you read my mind? Or was I coughing too much, or I don't know. Is it a sign, some kind of sign that I was coughing too much? Okay. Yeah, okay. All right, much better, thank you. So this actually tells us how to naturally merge the relational net idea or the skip bigram idea and then convolutional net. That is, if we can make this weighting function dynamic, right? So if the weight was all 1, you get the relational net. If your weight was, let's say, all 0 except for the local neighborhood, which is going to get 1, you get the convolutional net. If we can interpolate between these two, then you can get the best of the both worlds. And then that is what we call self-attention. The idea is that we're going to do the usual relational net or the convolutional neural net, but this weight in the summation is going to be determined by another neural network. So inside this neural net, we have a very explicit way of computing how all these vectors you get or the representation you get from all those possible pairs are going to be combined. And it turned out that it's very easy to implement it with the directed acyclic graph. What you're going to have is another relational network module that's going to look at the pair and then decide how similar or how relevant that pair is to the actual problem. And then we apply some kind of sigmoid function or the softmax function to get some kind of normalized weights. And then that's going to be our alpha xt and xt prime. And that coefficients is going to be multiplied to the output of the usual relational network before being summed up. Let's look at this. So if I want to compute the representation of this specific token, what I'm going to do is I'm going to compare every single pairing and then let this weighting function to give me a single scalar that's going to be multiplied to the actual vector representation of the pair. And then all these things are going to be summed after this weighting. And then we get the vector. And then now you see how you can get the convolution out of this, how you can get the skip diagram out of this, and then how this one is in fact interpolating between those two with respect to the problem that you're trying to solve. Because this weighting part is yet another neural network whose parameters are going to be adapted in order to maximize the performance of the problem that you try to solve. So it is able to capture the long-range dependencies, unlike the convolutional neural net. So that's a very nice feature because you don't have to stack all those layers in this case. But at the same time, it can also ignore irrelevant dependencies, unlike the skip diagram. So this one turned out to be really nice. It's a bit slow, as you can see, right? But anyway, so people have figured out that okay, you can generalize it further via, let's say, having a multiple heads. So you're going to have the multiple copies of these in parallel, or the multi-hop attention. That is, you're going to simply stack this self-attention layer on top of each other in order to build a machine that is able to see other parts consecutively. This is great, but there is a major weakness. Actually, there are two major weaknesses. First one is that the computation complexity of the self-attention is extremely high. It's quadratic with respect to the length of the sequence. And then if you think about, okay, applying this to paragraphs or the entire documents, it gets a bit, like the messy. It's very, very slow. Even though you can parallelize it, still the computation itself goes up, and then the computation, in fact, corresponds to memory use as well, largely in the case of the neural net, so it's not that great. And then second weakness is that it is not trivial for this kind of self-attention to learn things that can be really, that we think are really easy, such as the counting, simple counting of, how many tokens there are in this kind of sequence. It is not easy to compute it with the self-attention unless you use the universal transformer from the last week from DeepMind or the Google Brain. I don't know, one of them. But, that one is at the moment more hypothetical one. But so the counting is difficult. So that's where the recurrent neural net comes in. So the recurrent neural net is yet another node in the computational graph that's going to process the sequence in an online manner. So it's going to read the sequence one token at a time, maintaining its own memory. So it's going to have some kind of vector representation, and then it's going to update it every time it consumes one token. And then it goes all the way to the sequence, and then the memory vector you get at the end, which I use the HT here, that's going to be the representation of the entire sequence. And then it only took a linear time with respect to the length of the sequence, unlike the self-attention. And then having this memory, in fact, you can build you can show that the recurrent neural net with a lot of the assumptions and a lot of the very elaborate constructions. It's actually just a digital computer, essentially. So what we do with the actual, let's say, text RNN for the text classification is often that we are going to use a bidirectional recurrent neural net. So for the representation we're going to get at each token is going to be the representation from the first forward recurrent neural net that's going to, is forward, right, from your side. Okay, forward recurrent neural net that's going to get you the vector of the current token with respect to all the previous tokens. And then you're going to look at the backward or the reverse recurrent neural net that summarizes all the future tokens with respect to the current token. You concatenate them. That's the representation you get for the specific token. And then for the classification, you're going to either average them or do the max pooling to get a single vector there. Unfortunately, this is nice if you look at the computation complexity, but this processing is inherently sequential, unlike the self-attention, convolution, or skip diagram, which all could be done in parallel very nicely. In the case of the recurrent neural net, everything has to be done sequentially, so it's slightly less desirable for the modern parallelized distributed computing infrastructure. That's why the self-attention has picked up a huge, let's say, interest. And then, in reality, there are two major types of the recurrent neural nets, we call it cells, so the computation of each of the node. And then one of them is LSTM, and the other is the gated recurrent units. And then, like those are all implemented in the standard frameworks again, and also in the CUDA kernel and so on. So they are very efficient. You can just plug that in, and it's going to work. Now, so we have so far learned 5 different ways to extract a sentence representation or the representation of a sequence of the tokens. So we looked at the continuous back of word, and then we looked at 4 other ones that are going to take into account the actual order of the tokens. And then one thing you need to keep in your mind is that all these 5 things are not mutually exclusive of each other. You can always stack them or combine them together. And then recently, a lot of people have shown, so for instance, this is a pretty recent paper, pretty recent paper from Google Translate showing that if you combine recurrent neural net together with the SelfAttention, then you can get the state-of-the-art neural translation system. And then the second work by my PhD student, Jason Lee, he showed that you can use the convolution first and then recurrent neural net. Then you can build a fully calculable neural machine translation system with a very high efficiency. And then the nice thing is that all these are differentiable, so you just plug them in however you want. It's just like making a Lego or playing the Minecraft type of thing. And then you can actually let the framework take care of how to train this model automatically for you. So these are the 2 things that we have learned so far. Do you have any questions before we move on to actual language modeling part? I know. I'm like just compressing everything into I don't know, this 2 in total 4 hours, but 2 hours as much as I can. So do you have any questions? Can you now build a text classifier? Most important thing is that whenever you have the text classification problem, go to the fast text GitHub, clone it, and then try that first. That's often the hardest baseline to beat. So no questions? Where? Oh, okay. Oh, sorry. Yeah. Yes, so the question is, in the case of the attention mechanism, let's go back to the attention part. Here, when we compute the weights, so what are the things that needs to be considered to compute this weight? So the most vanilla version, in fact, takes as input the very same vector that's going to be used to, that's going to be fed into this relational net to get the representation. So, and then that's often we refer to it as content-based, let's say, weighting. But then you notice that, okay, there is no information of the actual ordering here. So what people have done is to add so-called positional embedding. So you're going to add specifically the value or the function to each of the vector here, so that depending on where it is, it's going to have a slight bias that differs from one location to another. And then that positional embedding can be used for this weighting function to, let's say, put more weight if they are close by, or put less weight if they are farther away. So there are a lot of possible ways to build this kind of thing. In fact, I highly recommend you to check out this latest paper from Google Translate, because this paper is essentially, okay, we're going to try everything possible and then see which one works best. And then they actually did find one that works really well. And then, in order to do so, they had to explain every single concept there. So, any other questions? Okay, let's see. Nope. Okay, there, yes. Yeah, so the question is, so we talked about the table lookup earlier. Let's see, where's my table lookup page? Okay, so we look at the table lookup here, and then what you notice is that you can pre-populate this embedding matrix by downloading those word2vec or the fast text embeddings and so on. Now, that's a good idea if your data set is small. Let's say if your data set is really small, then what can happen, especially in the natural language processing, unlike the images or so on, is that many of these unique tokens that you have are not going to show up in your data, in your training data, but they're going to show up in the reality when you deploy your system. Now, that can be a big issue, because if you have not seen a token, then you don't have an associated vector. And then often we're going to map that into so-called out of vocabulary or the unknown token, which is going to simply lump everything that you have never seen into a single token. So that's not that great. So in that case, what you can do is you can start by pre-populating this embedding matrix by downloading those pre-trained embeddings that was trained on a gigantic corpus, right? So how to get there, we're going to talk about it a bit later, and then pre-populate it. But then what you need to do is that you should not update this embedding matrix. You're going to fix this embedding matrix without updating it, because as soon as you update few of the token representations, they suddenly become incompatible to the other token representations. Now, if you have enough data, it's never a good idea to, in fact, initialize it to the pre-trained embedding, and because the pre-training often is done with another objective that you cannot guarantee whether it's related to your objective or not. So if you have, let's say, millions of the data points, then what you can just do is simply train the entire thing from scratch. So it's going to very much depend on your, let's say, availability of the data as well as the problem. Okay, any other questions? Okay, there's a question at the very end. Is that a question? Yeah. You have to shout. Yes. I know, that's why I prefer the skip bigram instead of the relational network myself as well. So, yes. So the question is that, okay, in the case of relation network, so what does this, let's say, relation network module actually compute, right? So that's the question. And then what kind of relationship does it capture? So we do not impose anything. So what we impose is that it is reasonable to look at a pair of tokens at a time, because the pair of the tokens is going to inform us more than just looking at a single token at a time. But now, what is going to be extracted from this module is going to be up to learning and data. So what does it learn? That depends on the problem. And then how do we investigate what has been learned? That is, in fact, the entire discipline in machine learning. That is doing the interpretation and visualization. Does that answer your question a bit up to some level? Okay. Any other questions before we move on to the actual language modeling? All right. So yeah, all right. No questions, right? This is a gigantic lecture hall. It's difficult to tell you though if there's a question or not. All right. So okay, I have like 52 minutes. I gotta like push in order to like pour out all the things that I know. Okay. So we're going to now finally talk about language modeling. So language modeling is perhaps the most important problem in natural language processing, because this modeling allows you to generate sentence, build a Q&A system, build a dialogue model, a dialogue generator, and so on and so on. But at its core, it's very straightforward. We're simply building a machine learning model that's going to take as the input a sentence or a paragraph, right? So we don't really care about the distinction between those because it's just a sequence of integer indices. And then we want our machine to output the probability of the sequence. Or if you don't like the probability itself, you can just say that, okay, you want your machine to tell you how likely this sentence is given some corpus, right? So you had a gigantic, let's say, text corpus. I want my machine to be able to tell me, how this new sentence is likely. So in other words, we want to build a model that's going to capture this distribution over the entire set of all possible sequences. And then unlike text classification, this is unsupervised learning problem. That is, we do not have any kind of target annotated manually or somewhat, right? So we don't have a target. All we have just inputs. However, it turned out that the best way to do the language modeling, this unsupervised learning problem, to solve this unsupervised learning problem, is to turn it into a sequence of supervised learning problems. And then how we do it is to use the paradigm of the autoregressive modeling, if you have taken the signal processing courses earlier, maybe like 10s or 20s years or the 30s of years before, then you probably remember this autoregressive sequence modeling or the autoregressive paradigm. The autoregressive paradigm, what it tells you is that, okay, in order to predict what the next signal is going to be, or what's the magnitude of the next time step signal is going to be, you look at the previous ones, right? So the previous observations are going to tell you what the future observation should be. And then in the case of this kind of distribution over a sequence, or the probability of a sequence, it can be rewritten as simply decomposing the probability over this sequence as a product of the next token prediction. So we're going to have the probability of the first token. We're going to have the probability of the second token given the first token. We're going to have the probability of the third token given the first two tokens. And then eventually we're going to have a probability of the last token given all the previous tokens so far. And then that's just, that just equality holds, right, exactly for any kind of distribution due to the definition of conditional distribution. But obviously, there must be one of them that is better than the others. But, we're going to skip that part for now because that does require discussion, some linguistics and so on that I have absolutely no idea. So we're going to just stick to left to right decomposition of autoregressive modeling. And then what this autoregressive, let's say, rewrite of the sequence probability implies is that it is now simply has become the sequence of the text classifications. So all the tokens before, so all the previous tokens, is a sequence of integer indices, which is exactly like a sentence. And then we are building a supervised classifier that's going to try to classify that prefix into one of the categories, where the categories corresponds to unique tokens in the vocabulary. So it's actually just a text classification problem, right? So this is a really important point. So does it make sense to you? So it's just really, okay, question there? Yeah. P of x1, yes. So the P of x1 is very straightforward. So all you need to do is you can estimate it without a neural net. So you're going to go through all the sentences in your Wikipedia. You're going to look at the first tokens, right? You're going to collect all the first tokens, and then you look at the frequency. That's the P of x1. So, okay, that one is not the classification. That's just collecting the data, and then you draw the histogram. That's true. And then there was another question around here, or maybe I missed. Oh, yeah, okay, there. Sorry? Oh, this really naturally incorporate that, right? So the question is that, okay, how does this autoregressive paradigm deal with the variable length, let's say, sequences? So if you look here, each one of them, so we're going to have just different number of the text classification problems depending on the length of the sentence itself. But each of the text classifier, we can use a single text classifier that's going to be shared across every single location. So this paradigm actually allows us to build a single text classifier in addition to the, let's say, unigram first token probability distribution, right? That's going to deal with the sentences of any length. All right, okay. So what this means is that whatever we have learned so far on the text classification can be used as it is to build a language model of your choice. Now, so let's see, what it means is that all we need is just a single neural net text classifier that's going to take as the input a sequence of previous tokens as the sequence of integers, and then they are going to be turned into the vector representation. So you get a sequence of vector representations of the previous tokens, and then you can use any one of the 5 text representation modules that we talked about to get a single vector that's going to be fed into some arbitrary subgraph that's going to output a real values. So how many of them? As many as there are unique tokens in the vocabulary. And you apply the softmax function to see actual representation. So it's really straightforward. And then how we talked about training this text classification module, that is to minimize the negative log probability of the correct answer given the input, right? Or to maximize the log probability of the correct answer given the input, applies exactly here. And then this is going to be our loss function. And if you look objective function, and then if you look at it, that's precisely what the autoregressive modeling tells you to do. So we are, in fact, trying to maximize the log probability of the sentences you see in the training corpus. Right? So training this classifier corresponds to trying to maximize the probability of the sequences that you see in your training set while minimizing the probability of the sequences that are not in your training set. So it turned out that all you need is just a text classifier with all those various, let's say, text representation module, and then you can now do the language model, and then soon, if time permits today, I'll be able to show you how to build a translation system as well. Now, once you have this kind of language model, you can now use it to do various things, and then the most natural thing is to score a sentence. So let's say, you know, like we have some simple example of, let's say, in Korea, more than half of the residents speak Korean, which I guess is true. Then how we are going to use this system to score this sentence is to first, we're going to look at how likely the first token in is. And then next, we're going to look at how likely this Korea is given in. And then we're going to look at how likely more is given the in Korea. And then we do it over and over until the very end. And then on the way, we get all those log probabilities of the next token given all the previous tokens. What you need to do is you just sum them, and then you get a log score of your sentence. And then now you can think of, actually, you can go a bit wild, and then you can think of building a Q&A system out of this, right? So let's say my question is, which language is spoken in Korea? Then I can think of building this kind of sentence a lot and a lot by just replacing this Korean with the different languages, right, including Korean. And I'm going to let my language model score each one of them. I'm going to pick the one with the high score. And then if that contained the Korean, then I'm going to say, the answer is Korean, right? So that's the power of the language model. If you have the perfect optimal language model, that allows you to answer a lot of things that require, vast amount of knowledge, as long as you have used a large corpus. And then the nice thing about this language model is unsupervised learning. You can get the data pretty nicely and easily. For instance, one thing you can do, you go onto the Wikipedia, just download the latest dump. Then that's actually a very large corpus. Of course, for the English and then few other languages, not for all the languages. And also, if you work at any kind of social media site or so on, you can also scroll them. And then there, you get actually more variety of how the people speak their everyday language, right? So it's a very nice way to collect the data and then build a system. So you can score them. That's really nice. But then, we're going to take a bit of a slight historical tour of how people have been doing this language model, because it's pretty clear that, people have been doing this language model, like this since a long time ago. It's probably not that the Yoshio Benjo invented the whole problem of the language model. He solved it. He didn't invent the problem. So let's back up a little, and then, let's talk about what we would do without a neural network. If we didn't have a neural net, what would be the thing that I would do, right? The first thing that people have done, and then people still do, is to assume some kind of Markovian property. So the Markovian property tells us that my distribution of the next or the new value, right, new potential value, should only depend on a finite window of the previous tokens. So in order to do the correct autoregressive language modeling, what we had to do was estimate this probability of the next token, let's say at time step t, given all the previous tokens. Well, we're going to simply say that, it's Markovian, so it's going to only depend on the n-1 or the n previous tokens only. And then we're going to ignore the dependencies further back. And then that actually is nice in various ways. So I'm going to talk about that a bit soon. So what it means is that we are simply saying that, local context matters, but the global context doesn't really matter that much, although it doesn't mean that the global context is not captured. So the local context matters, So local context clearly matters. You can see from this equation. But then we're going to say that, because explicitly modeling the global context is difficult because of the reason that I'm going to talk about, what we are going to do is we're going to let this entire, let's say, product of the probabilities to indirectly capture the global context. So this is how people, approach the language model. back in, let's say, 80s and 90s and or even nowadays. But then, once we do that, what we need to do is we need to estimate n-gram probabilities. So given the n-1 or the n previous tokens, what is the probability of the next token, right? Or what is the distribution over the next token? And then if you recall the definitions of the conditional and marginal probabilities, we can rewrite this conditional probability as the joint probability, right? Probability over the n or n plus 1, let's say many consecutive tokens, over the joint probability of the context, so the conditioning, let's say, tokens only. And then the denominator, you can rewrite it by simply summing over all possible next tokens from this joint distribution, right? So definition of conditional probability, definition of what the marginal distribution is. And then where the V here is the vocabulary of all possible tokens or all possible unique tokens that we talked about. Now, how do we estimate this? Earlier today, you probably learned about all those different estimation principles, going all the way to the variation base and so on, but we're going to simply stick to the, let's say, maximum likelihood estimation for now. And the maximum likelihood estimation, everyone knows, so I probably don't need to explain it too much, but it consists of the two steps. One is that we're going to collect the data, so you can think of, tossing the coin as many times as you can, right? So you're going to toss the coin a lot. And then that's the data collection. And then once the data has been collected, you're going to do the estimation by looking at how often that coin landed heads. Right? So we can do the exactly same thing, same kind of thing for language model, n-gram language model as well. First, we're going to collect the data by crawling the Wikipedia, news articles, tweets, whatever the resource that is available out there. So that's going to be your data collection. That's almost like the entire humanity kind of collectively tossed a coin for us, right? So that's really great. So we have all those data. And then now we need to estimate it. So what we need to estimate is first, we're going to estimate for all the n-grams, how many times each n-gram occurred in the data set you have collected. And then next, what you need to do is you're going to look at how many n-1, the context part, occurred in the entire set. So it's just a simple counting. So you're going to build a gigantic table that's going to contain all those counts. In reality, of course, you don't build just naively the table, because you can build all those tree and then advanced data structure to make it more efficient. Once you have those counts, then what we can do is maximum likelihood estimation principle tells us that we can estimate this quantity by simply replacing each of the probability here with the actual counts. So we're going to look at how many times this entire thing occurs, and then we're going to divide it by how many times this entire thing, while changing the last one, occurs. And then, this makes sense, right? If it doesn't, then, we'll probably have to spend a lot of time on this to make sure that everyone is on the same page. So examples are always good. So let's say I want to estimate how likely university is going to follow a phrase New York. What I'm going to do is, first, I'm going to count all the occurrences of New York University in, let's say, Wikipedia or whatever the corpus you have. And then now I'm going to count all phrases that starts with the New York and ends with some words, right? So there will be New York State, New York City, New York Fire because of the New York Fire Department, New York Police because of the New York Police Department, New York Bridges, so on and so on. I'm going to just count all of them. And then what I need to know is, okay, among all those New York something, how many were actual New York University? That is precise the probability of university given New York. So you see why all those counting matters, and then once we have the count, then we can actually compute these n-gram probabilities quite efficiently and then rapidly. So the memory use grows quite significantly, but it's pretty nice. Now there are two problems that you may have already noticed. The first one is the issue of the data sparsity, or equivalently, the lack of generalization. Let's say you're given, so after training your n-gram model, you're given a new sentence that is, a lion is chasing a llama. If you don't know llama is this looking, let's say, animal which lives in the South America, right? So lions, llamas don't really live in the same continent, so you rarely get to see the actual sentence where the lion is chasing a llama. And then if you go into the Google Ngram Viewer, so Google has the awesome service called the Ngram Viewer that actually computes the n-gram probability of the whatever the phrase you give based on all the text from the Google books. That's pretty awesome. But weirdly so, chasing a llama has never, that phrase chasing a llama has never been used or never been written, at least in English text. So what happens is that the probability of this sentence, a lion is chasing a llama, according to our n-gram language model, is going to be 0 because a chasing a llama, this single phrase, never occurred in the training corpus. It just never occurred. Well, they're going to probably change it, right? Because, I'm going to put this slide is going to go on the online. Google is crawl it. It's going to update its n-gram language model. So, on Thursday, there is, I think, the AI ethics session. I'm pretty sure you're going to hear about it. In reality, because of the feedback, it's always never trivial to, build your machine learning system or make your slides, right? Because it's going to get fed in, you have to update it. So, okay, so that's definitely a problem. But then, some people ask me, but is that actually a problem? Isn't it just what the maximum likelihood estimation with a given data set should do? But then, you got to think about, okay, so clearly nobody saw a lion chasing a llama, but somehow we can generalize. We can somehow systematically generalize to this new situation without having observed it directly. So in that sense, because, at the very beginning, I said that, okay, I'm going to kind of, let's say, throw away all those, let's say, assumptions about the equal distribution between the training and test set, IID, or so on, right? So this is actually the problem that we need to tackle, especially in the natural language processing. Zero probability is not good. And then the second thing is that this n-gram language model, due to the Markovian assumptions that we have, it has a really hard time capturing long-term dependencies. So one example from the Stephen Clark from the Google DeepMind nowadays. So let's take a sentence. The same stump which had impaled the car of many a guest in the past 30 years and which he refused to have removed. So this is a sentence. Now let's say I want to predict the probability, or compute the probability of remove, the last token. And then if I use the 4-gram language model, so looking at the 4 previous tokens, then it's very, very unlikely that I'll be able to tell that, okay, removed is the one that has to be there. It's very difficult. It could have been any verbs there, right? Past particles. But then, if my n-gram language model or my language model was able to see this stump at the very beginning of the sentence, then it becomes kind of pretty obvious that it's going to be removed. Because the stump should be removed, right? So this kind of, let's say, long-term dependency cannot be really explicitly captured by this kind of n-gram language model. Now let's see, how people have solved before. So the first one, data sparsity. So the data sparsity issue is that, in some cases, this count of this n-gram is 0. So what you can do is you can smooth it very simply by simply adding some epsilon. So you're just assuming that there is no n-gram or the phrases that never occur. So it's actually pretty Bayesian there. So we introduced the prior there, right? So the prior is that nothing ever occurs 0 times. Everything occurs for some time. We put a very simple uniform prior there, and then it becomes a penalized maximum likelihood estimation. But this is slightly less the satisfactory because it's going to put some mess, probability mess, to all those nonsenses that will never happen. So you can be a bit smarter by doing the backoff. So instead of, let's say I'm looking at the 4-gram here. Now, okay, this never occurs. Then what I'm going to look at is that I'm going to cut one word down from the previous tokens. And I'm going to look at the trigram. Then the chance of seeing some occurrence goes much higher. And then you're going to use that number as some kind of guide to get some rough estimate of what the 4 grams count should be. And then obviously, simply using that does not get you the actual normalized probability, so you want to adjust it by introducing additional parameters that you can estimate. So at the end of the day, the most widely used approach based on both the smoothing and backoff is the Kneser-Ney smoothing backoff algorithm. And then again, you do not implement it yourself. That's a suicide. What you want to do is use the KenLM. So you're going to Google KenLM, which was created by Kenneth, who is now at the University of Edinburgh. And then it has potentially the most efficient implementation of the Kneser-Ney smoothing backoff-based n-gram language model. On the entire Wikipedia, it's going to take only about an hour or 2 to run it, on like the machine with a decent number of the CPU cores, and then it's going to get you the score, let's say, almost immediately. It has a Python interface, C interface, and everything, so it's very easy to use. Now, but how about the second problem, long-term dependency? There is no traditional solution, unfortunately. It's impossible to avoid this issue because as you increase the n, so you can increase the n to capture all those long-term dependencies you might think, you might hope, but then what happens is that you run into the first problem with the data sparsity. Now, given a fixed number of the sentences or sequences in your data set, as you increase the n, because all possible phrases, the number of all possible phrases increases exponentially with respect to that n, essentially you're decreasing the amount of the data. The coverage decreases exponentially as well. So you cannot really indefinitely increase n unless you know that your data size is going to grow exponentially as well, or the coverage of that is going to grow. But that's never going to happen. In other words, these two problems are really closely related, and then it's impossible to solve both problems simultaneously. If you want to capture long-term dependencies, n has to be large, but to address the data sparsity, n has to be small. So it's two conflicting goals that we have. Any questions about the traditional solutions? I mean, the answer is that you just download KNLM, run it, it works. It's actually really great. I still use it these days. It doesn't take too long and anything. But then, this is about the latest techniques. So let's move on to the next one. So then, in 2001, or in 1999, Yoshua Bengio and his collaborators back in Montreal, and it's still in Montreal actually, realized that so we can first tackle the first problem and the second problem simultaneously if we replace the table-based, so counting operators, with the neural networks. And then this is the thing that we already saw, right? So we build a neural net-based text classifier that's going to take as the input previous tokens, and then outputs the distribution over the all possible next tokens. So we already know how to do that, and then you train it by using backpropagation and SGD, and then now this network is going to now generalize to an unseen n-gram. So the n-gram that never appeared in the training set, this neural net is not going to give you the 0 probability, but some reasonable probability. And then that actually addresses the issue of data sparsity. Now, how does it do it? Let's think about, why the data sparsity happens. A kind of shallow answer that I have is that, some n-grams just do not occur in the training set at all, while they do in the test time. So that's the problem, right? Now, if you think about a slightly deeper answer, the deeper answer is that it is difficult to impose some kind of token or phrase similarities in the discrete space. So when you have those integer indices that are all, let's say, independent from each other, it is not easy to define the similarities of them. I mean, first of all, it's a discrete space, and then we actually don't know about the similarity of the text that much, right? So if you consider this slightly deeper answers a bit further, now you can think of, so how to avoid this issue with the data sparsity. So if you think about the earlier example of, the llama being chased by the lion, now the problem was that the chasing a llama never really occurred in our training corpus. On the other hand, if you think about it, chasing a cat occurs, chasing a dog occurs, chasing a deer occurs, all those occurs a lot of times. So how we actually generalize, how we as humans generalize from the chasing a cat, chasing a dog, chasing a deer, to the chasing a llama that you have never seen before, is to notice the similarity between the llama and a cat, dog, or deer. Because we know that the llama is a mammal with the 4 legs, and then it looks kind of similar to deer, we know that chasing a llama is very likely when the chasing a deer occurs quite a lot. So if we can also build this language model so that it knows llama is a mammal similar to cat, dog, and deer, then it will be able to guess roughly that chasing a llama is pretty much likely as chasing a cat, chasing a dog, or chasing a deer. It turned out that this neural n-gram language model, or any kind of language model that we're going to talk about based on neural net, automatically addresses this issue by learning this kind of similarities in this continuous vector space that this network learns from data. So we have two types of the continuous vector space here, in fact, three of them, is that the one after turning the token, so the integer-based representation of token into the vector representation. So that's going to be our token vector representation. And then one after getting the sentence representation, we get a single vector. It tells me the similarity, tells me about the previous tokens. And then in that space, the neural net learns some continuous similarity function or the metric that's going to capture the similarities of the actual tokens as well as the phrases. And then once you do that, because the neural nets are pretty smooth actually. So if you perturb a bit here, then the output is going to be perturbed in a similar way. You perturb it here, output is going to be similar way. So if it knows about all those similarities, then similar phrases or the previous let's say tokens will lead to a similar distribution. And that's how this neural net exploits all those similarities to generalize to unseen n-grams. Still, kind of, it doesn't really, it's not that clear, right? So let's take a very, very simple, the simplest example you can think of. So we have 3 training examples. There are 4 qualification, 4 teams passed the first round, and 4 groups are playing in the field. So 3 sentences. And then what I want to know is that I want my language model that was trained on these 3 sentences to tell me what's the probability of groups following the 3. Now, 3 groups never occurred in the training set, so the usual count-based method is going to tell us that, okay, 0 probability that there can be 3 groups, right? But then, what happens with this neural net? So there's the first example, consider the 3 teams, right? So this 3 token is going to become a token vector representation, and then we're looking at the bigram at the moment, so that token representation is the representation of the entire context. And then from there, it's going to try to predict a distribution whose mass is concentrated on the teams, right? And then now, the second example is the 4 teams. So this neural net is going to try to output a distribution whose mass is concentrated on teams, again, given the input 4. And then what is the efficient way to do is to map 3 and 4 nearby in this continuous vector space, so that from there, the same mechanism can be used by this neural net to output the same kind of distribution. And then you notice that the third example, there is 4 groups. Now what it's going to do is, notice that, 4 and 3 cannot be exactly the same because now the probability distribution outputted by the neural net, given the 4, is going to need to put large enough mass also to the groups, right? So it's going to make a slight change, right? It's a continuous space. Unlike the discrete space, you can make as infinitesimal change as you can, and then trying to adjust the all weights so that the given 4 is going to output a distribution to put equal masses to the teams and groups, right? Now, in this case, if we feed in 3, and then trying to see the probability assigned by the neural net to the groups, because 3 is close to 4 and the neural net is smooth, what we get is the distribution that is not going to put 0 probability to group, but some reasonable probability to group. And then that is from the similarity between the 3 and 4 that has been captured by this neural net by looking at this data. Because the 3 led to the teams, 4 led also to the teams, they should be similar, and then 4 led to the groups, so 3 probably leads to the groups as well. So this is how the neural nets in the continuous vector space captures these similarities and then use it to generalize to the unseen n-grams, unlike the count-based assay methods. So in practice, what you do is that you collect the data, right? You collect the corpus, collect all the n-grams, shuffle them to make it look like the IID data, build a training set, train the neural n-gram language model, which is simply training a text classifier, right? Using the stochastic gradient descent of mini batches containing 100 to 1,000 n-grams. And then again, you do the early stopping based on the validation set. And then the validation set should come from the future articles, right? And then you report the perplexity on the test set. Now, what is perplexity, right? So I never talked about it. But if you look at the perplexity, what it's computing is essentially the exponentiating the loss function. There was the log probability or the negative log probability. And then what it corresponds to, this perplexity, tells you a very nice story about how many potential candidate tokens your network considers before the correct token comes in. So if someone says that, okay, my language model's perplexity is, let's say, 50, what it's saying is that the correct token is going to be within the top 50 tokens that the language model, like the thinks is correct for the next token representation. And then what it means is that the lower perplexity, the better, right? So, if your model is extremely confident about everything, its perplexity is going to be 1 because it's going to get everything correct in the first guess. If it's not confident, then its perplexity is going to be high. If the perplexity 10 means that, okay, your neural language model needs to consider top 10 candidates until it hits, on average, the correct token. So that's usually the thing that people report, but I don't know, does that really matter? I don't know, you can use the same low probability and then just say that, oh, go up, and then it's just nets, right? So any question at this point? No? Oh, sorry, yeah. I'm sorry, it's a gigantic, like lecture hall, yeah. Okay, yes. Oh, thank you. Yes. Mm-hmm. Yes, yes. Right, so the question is about the domain adaptation. So let's say you build a text classifier on the news articles from the South Africa, and then you try to apply the text classifier to the news articles from another country or another region, then you actually do see noticeable drop in the performance. Now, that's the issue with the domain adaptation, and then that's a kind of, again, like the entire discipline on its own under the machine learning. And then in that there, so these neural nets actually do give us a very nice way to do the transfer and then fine-tuning. So for instance, one thing you can do is that you start from the very well-trained text classifier, but then you're going to collect a small amount of data on the target domain and then trying to fine-tune it a bit. So often that helps if the goal is to simply to apply to the another domain. And then if you see that there are many domains in the future that you need your model to be fine-tuned rapidly, then you can actually use some of the latest techniques from the meta-learning to train the model to be well adapted to the new domain in the future. In fact, on Thursday, I am going to talk a bit about the multilingual translation system with the meta-learning, so you'll probably have to just show up. 8:30, I know. Yeah. Yeah, so then I'm going to talk about that, yes. Okay. Right, so the question is, if you think about this language model, especially with the neural language model, what you see is that it does not only capture about the language itself, like the syntax, but it also captures the semantics, right? So there is the knowledge about the meaning of the words, and then that actually corresponds a bit, or it reflects the word knowledge as well. Now, do we want to separate it or not? People do want to separate it, right? So think about that some of the examples by the Chomsky, you can always come up with a syntactically well-formed sentence that is absolute nonsense, right? So then, should our language model assign high probability to that nonsensical yet syntactically well-formed sentence, or not, right? So so far in practice, we haven't really done much of that separation, perhaps because the separation is not really there. We don't really know the separation. So no, the answer is I don't think anybody is actually doing that explicitly. It's like trying to get out the grammar and then others. But of course, you can look at some people who are working on the grammar correction type of thing. There, you need to really separate out the grammar from the actual content, right? You don't want to change the content. You only fix the grammar. Okay, yes. Okay. Right. So I'm going to actually talk about the more neural language models shortly. I'm almost there, but but yeah. So in order to avoid the issue with the counting, so what people have been doing is, for instance, okay, if I can group or the cluster the tokens meaningfully, then I can actually reduce the state space size, and then that can actually help me generalize to unseen n-grams in the future and so on. So some people have used that kind of, let's say, external knowledge to get a clusters of the tokens in order to do a better, or the, like the language model that generalizes better. So, using the kind of word net hierarchy to, like build the hierarchy of the clusters and then use that information to do the clustering, language modeling, yes. But what's happening is that if you look at these, like the representations that are retrieved from the n-gram language models, you actually do see that these representations do capture them automatically already from the corpus. So that's how it generalizes. Any other questions? We still have like 20 minutes, or 15 minutes. Okay, gotta push. Okay, here we go. Yes, another question. Right. Okay. That's a really interesting question. So the question is, how do you tokenize? Let's say, let's find one. Okay. So here, if I simply naively say that, okay, I'm going to separate each sentence using the white blank spaces, right? Blank spaces, and then I'm going to consider those separated out things as tokens. What happens is that I'm going to get qualification period as a single token. And then if there is going to be qualification alone later on, then somehow I'm going to have the qualification and then qualification punctuation mark concatenated. And we don't want that, right? So usually you want to do so-called tokenization in advance. And then the tokenization routines are nothing standard or anything, but there are some set of the toolkits such as the SpaceIO or the NLTK that you can simply download and then apply for each of the languages. And then those tokenization routines are going to, let's say, tokenize out, like the different punctuation marks or normalize the punctuation. So there are a bunch of things that you need to do, right? But that is going to depend on which language you're talking about. So for instance, all this tokenization doesn't mean anything if you're working with, for instance, Chinese. There's no blank spaces to start with. And then there's very few punctuation marks. There, what you need is separate segmentation algorithm that's going to separate out into the different words and then do something about it. And then if it's Korean, then, again, the different thing happens. And then depending on which language you're working with, that's going to have to be decided. But if you're working with the major languages, my suggestion at this point, use the SpaceIO's tokenization routine. That works really well. But that is free for the research and non-commercial uses, but if you want to make a startup out of it, you'll have to pay the license fee. But like they take care of all those, let's say, nasty details about the tokenization. So I highly recommend you to try it out. Yeah. And I'm going to talk about it a bit later when I talk about the machine translation later, as in on Thursday. Yeah. Any other questions before we move on? Like 10 minutes, I can actually cover a lot. All right, so let's cover a bit. Yes, more. All right, so this neural n-gram language model was amazing idea, except that, except for the Holger Schoen, who is now at the Fair Paris, but was a professor at the Le Mans University in France, except for him, nobody really used it. So then, but in the background, in the machine learning community, we've been actually working more and more to get the better and better language model, going beyond the n-grams. So one thing you can think of it is that, okay, n is a bit problematic. I want to increase the n, but my neural net is going to grow, right? So how can I actually increase the context size n without having to grow the language model too large and then keep the computation as efficient as possible? And then there comes the idea of the convolutional language model. By using the dilated convolution, we can rapidly increase the window size. So by doing so, using the dilated convolution, we can increase the window size exponentially as we stack them, and then that allows me to, increase the context size very rapidly without having to introduce all those parameters and the computation. Now, one thing we have to be careful when it comes to language model, unlike the text classification, is that we have to follow the causal order of how things are generated, right? So we cannot really look at the future tokens in order to predict the current token, because then the problem becomes trivial, and then the autoregressive paradigm just does not work anymore. So in this case, you have to be a bit smart about how to mask out the parts that are future in order to predict the current token using only the previous ones. But using this kind of dilated convolution turned out to be extremely effective and then, efficient as well. And then this idea is behind all those recent successes, such as the ByteNet for the character level language model, Pixel CNN for the auto-regressive modeling of the actual images, WaveNet that is actually used on many of your cell phones already to do the speech synthesis. And then I heard that that's the reason why the DeepMind can still sustain. But okay, so that is, and then you use a gated convolutional language model, and then these all are used for in practice, mostly on your phones as well. But then you say, but the context is so limited, right? So however many convolution layers you're going to put in with the dilated convolution is still a finite context. You cannot go to infinity. But what we want is infinite context, right? So then you can think of, okay, among the 5 different, let's say, sentence representations, you see that actually the convolution was the one with the finite capacity or the receptive field size. On the other hand, all the others didn't really care about the length of the sentence. So maybe you can think of okay, let's try continuous back-of-word language model. We're going to have all those previous tokens and then compute the average of the token representation, from that trying to predict the next one. Sounds like a good idea. Unlike text classification or the categorization, it turned out that this one really doesn't work well. The ignoring the order really hurts when you're trying to generate or to predict which tokens should come in order. Not surprising, right? So, and then, for instance, wait, let me see. What was the example that I gave? So, for instance, as the context window, the size of the context window matters, because as the context window gets larger, for instance, in the SVO, subject, verb, object, like the English, the verb becomes less and less likely, but continuous back-of-word just cannot capture that easily, right? So there are many issues with the continuous back-of-word language model, except that the Deceivo language model turned out to be amazing at getting a good representation of the tokens. So people use these continuous back-of-words to get the token representation you can use in the future to solve the problem where you have only a small amount of data. And then again, you don't do it yourself. Token representation, fast text representation is just amazing. It's just kind of crazy good. So you just download it and then use it. So in reality, to do the infinite context language model well, already in 2010, Tomasz Mikolov and others proposed to use the recurrent neural nets to do the language modeling. And then what the recurrent network does is to summarize the tokens that it has seen so far into a single memory vector. And then that is very efficient online processing. And then this is precisely what we do, especially when we listen to someone saying. What we do is we're going to listen one token at a time, update our memory state, and then we're going to either trying to use that information to do something or trying to predict what the other person is going to say. That's kind of predictive coding. And then if you do the neuroscience literature, it actually does happen quite a bit. And then now, it consumes constant time per step. That's great. And then it has a constant memory need throughout the entire processing. So it has become pretty much standard in the language model in practice for the speech recognition system, machine translation system, and also the autocorrect on your phone as well. Especially if you're Samsung, I think they use the recurrent language model with the characters. But if you don't, then the Google also started to deploy it, but I'm not sure whether that's recurrent neural net. All right, so then the nice thing is that recurrent neural net is good, except that there is a huge burden put on the recurrent neural net. It needs to memorize all the necessary details for predicting the next one from the infinitely long context. And then now, because these memory vectors are real valued vectors, it's pretty high dimensional, several hundreds to several thousand dimensional vectors, you can really cramp in anything you want, but whether we can learn such mapping, and then whether we can learn a mapping that's going to decode out the information from that to predict the next one is a big question, especially with the final amount of data. So then we can use now the self-attention together with the recurrent neural net. Now, recurrent neural net is going to give us the representation of each token that summarizes all the previous ones. And then we're going to use the self-attention to rapidly or to readily access all those faraway informations. And then in Kotran, who used to be at the University of Amsterdam and then who is now at, I forgot actually, where is Carl? Okay. Who was at the University of Amsterdam, who is still there, he's going to defend his thesis this November. What he showed was that you run the recurrent neural net, but then you do the self-attention together to get the best of the both worlds. So the recurrent neural net is going to get you all those high-level, let's say, concepts from the long-range, let's say, things, and then we use the self-attention to read directly from all those previous tokens to trying to see what are the necessary things for the next token prediction. Now here as well, we have to ensure that we do not look at the future. So we have to be quite smart about this masking out the parts that are computed based on the future context. And then he called the recurrent memory network. And then recently there's been a couple of papers showing that you can use the self-attention alone if you stack them enough to build a good language model as well. Now we have learned what autoregressive language modeling is, and then how this turns the unsupervised learning problem into a series of the supervised learning problem. And then recently people started calling this self-supervised learning. I'm not really sure about that because these people want to always introduce a new term, but how many of them actually survive, right? So, and then we learned about how the neural language model improves upon n-gram language model. The continuous vector representation facilitates generalization to unseen n-grams that allows us to use a larger n-grams, and then that captures all those similarities. And then now we learned that using the self-attention and the recurrent neural nets, we can in fact use the infinitely large context window. Now, so I have 4 minutes and 40 seconds. But I have another 2 hours on Thursday, but at least what I have covered today is very kind of, let's say, underlying fundamental ideas behind the text representation. So on Thursday, I'm going to actually talk a bit more about a bit of a math behind the backpropagation through time, and then where all those gating ideas came from, and then talk about the machine translation and the recent advances. So some of the latest research topics, such as can we do the non-autoregressive language model, or can we do the multilingual translation with the meta-learning type of the idea, and then how we actually do some kind of real-time translation if necessary. And then with that, I'm going to get some, let's say, 2-3 questions, and then wrap it up. So do you have any questions? No? Too clear? Yeah. Oh, there you go. Yes. Yep. Okay. Yeah, so so the question is, so we all assumed, I assumed at the beginning that, we're going to build a vocabulary of all the unique tokens from the training set, right? Because the test set and the validation sets are supposed to be articles from the future. We don't have access to that, so we need to build a vocabulary using the training set. Now, what happens if you run into a token that is not in the vocabulary, right? That's a big issue. Now, there are a number of ways to handle that. So one way is that what if we go for the character level modeling, right? So instead of looking each of the token as a separate thing, we see the token as a sequence of letters. And then in fact, that's exactly what we do. We never see the token as it is, but the token is going to be a sequence of letters or the fonts, right, as we hear. Or, there are some people have actually tried using the dictionary definition. So what if we have never seen this token, but we get the definition of that, right? That's also how we actually handle a new token as well. Then can we replace that table lookup layer with another neural net? So it's going to be a small subgraph that's going to consume a sequence of dictionary definition tokens, and then gets us the token vector representation. So it is a very active research area. So on Thursday, I forgot to mention, but I'm going to talk about the character level translation in the context of the multilingual translation. There, it does generalize to the unseen tokens quite often by doing the transliteration, or they're trying to guess from the how the similarly spelled words are used. Yes. Can you say it again? Yeah. Oh, yeah, okay. So the tokenization, right? So the tokenization is really troublesome. So the question is that, okay, so for specific languages or for specific other languages, the tokenization will have to differ. So how do you handle that? Now, tokenization is troublesome. And then we are always striving to remove any kind of need of the tokenization. So in fact, I am going to talk about the character level modeling on the Thursday, where we do not need any kind of tokenization, and then still the model is able to handle multiple languages simultaneously. And then they all have the different, let's say, inflectional structures, morphological structures, and still this kind of neural net, because in the continuous space, it's not only capturing the semantic similarities, but also the syntactic and all those typological similarities. It can, in fact, generalize and then work with the multiple languages. So I'll get to that. But in short, in practice, what you need to do is you really need to find the people who have worked on all those tokenization and then script and then trying to adapt it to the new language that you're working with. So it's a pretty tedious manual process, but that is really crucial to building this kind of system. So all these things, these boxes are outputting some kind of, let's say, several hundreds or several thousand dimensional vectors. So that is some kind of embedding space. But of course, if you want to say embedding space, you have to, let's say, ensure that these follow something. But we don't really care because, these vectors are going to be used by this neural net, the following, let's say, computational graph. So this is the embedding space. It's a continuous embedding space of all those discrete entities. Now, and then there are multiple layers of that, both spatially and then hierarchically. Yes. It's slow. So the character level model is all good. It works amazingly well. It's slow because essentially the length of the sequence, now, okay, it's all the same sentence, but length of the sequence differs depending on what kind of tokenization strategy you use. If you use a character level model, it's really, really long. It just takes a long time. But, if you wait a bit for the NVIDIA to come up with the next generation GPU, we can always, work with that. And I guess for that, I'm going to wrap it up. Thank you.